students, let us discuss free vibrations, forced vibrations and resonance. This point is included in the chapter Oscillations and Superposition of Waves also. The phenomena of resonance we have to use in the chapter number 13, AC circuits. So in this regard, this point is important. For the study of this point, we take the examples of oscillatory motion. So the first example we take of simple pendulum. This is the equilibrium position of the simple pendulum. If the pendulum is displaced from its equilibrium position to position A and released, then it starts oscillating along this path. This path is slightly curved here. So these vibrations of pendulum of its own, it vibrates due to because of own restoring force. The oscillations or vibrations are because of its own restoring force. So such vibrations are called free vibrations. So we can note that point in the first point of free vibrations, that free vibrations are vibrations under the action of own restoring force. So very simple definition. That point we have studied in detail in oscillations, that for the oscillatory motion force is necessary. That force is the restoring force. Here free vibrations are the vibrations under the action of own restoring force, and the frequency with which the vibrations take place is called as the natural frequency. The frequency of free vibrations of body or pendulum or any object which is having free vibrations is called natural frequency of vibration. So you have to remember this point. This is new point here, is natural frequency. We have called it simply as a frequency. Now in this point we call it as natural frequency of vibration. Let us denote this frequency by Fn, natural frequency of vibration. So when these vibrations take place, there is loss of energy continuously in the medium in which the body is placed. Here pendulum is placed in air. Air has some frictional resistance. So energy given by us initially, that energy goes on losing or goes on decreasing. There is loss of energy in the air due to frictional resistance of air. So here we can note the third point. There is continuous loss of energy due to frictional resistance. This frictional resistance of surrounding medium. If there is surrounding medium as air, or it may be any fluid in which the system is placed, then that is exerting some frictional force, and due to that there is continuous loss of energy. As there is continuous loss of energy, we observe in the pendulum that amplitude goes on decreasing. Amplitude of vibrations go on decreasing. There is no constant amplitude. So these points we can note in case of free vibrations. Now we have to go for the forced vibrations. For the forced vibrations, we consider the examples in our day-to-day life. First example we take of if you have observed it, of a flour mill. In a flour mill, that mill is a rotating machine. So when it rotates or when it is in working, then the parts nearby the mill vibrate. Those vibrations are forced vibrations. Also, any type of machinery in which rotating bodies are there, or it is a rotating machine, then nearby points vibrate. Those vibrations are forced vibrations. Again, one example we take here. Suppose there is a hollow box. And to the hollow box there are two holes. Here, and if we held a tuning fork on it, and this tuning fork is vibrating. This the vibrating tuning fork is held on the top of this hollow box. Then here this top surface, this surface vibrates. There is vibration to the surface, as well as the air particles inside the box also vibrate. Those vibrations are forced vibration, because the particles of air or this top surface are vibrating under the action of this vibrating tuning fork. Actually, this tuning fork is the external body. It is not the part of hollow box. Tuning fork is different body. Hollow box is one body. Suppose this is another body. If this vibrating tuning fork is kept on the surface and it is held vertically like this, so that its stem is in contact with the surface, then its vibration or its energy is received by this surface of the box as well as air particles inside the box, and they start vibrating because they gain energy from the tuning fork, and then they start vibrating. Those vibrations are forced vibrations. So here we say that energy is given by tuning fork to the box and other parts of the box. Here, so here this tuning fork acts as external agency. It is also called as, we are supplying external periodic force. So to observe the forced vibration, we have to take some externally vibrating body or external periodic force, if it is near to the given first body or the body which is under observation, then we can observe the forced vibrations. So again I explain in brief that here there is one body which is hollow box and another body is the tuning fork. If it is vibrating and it is held with its stem in contact with the wooden block, then it gives its energy to the top surface of this box, so that the surface as well as other parts in the box, means air particles, also start vibrating. Those vibrations are forced vibrations. These vibrations are due to the tuning fork, means due to external periodic force. So we can define here forced vibrations. Forced vibrations are the vibrations under the action of which force? Due to external periodic force. External periodic force. Simple definition: one body vibrates due to the presence of another vibrating body, and the vibrations of one body, means first body, are called forced vibrations. Now here the vibrating tuning fork is called as a driving body. It is called as a driving body. Here the frequency with which this box vibrates or surface vibrates, it is equal to the frequency of this tuning fork. So here the frequency with which frequency of vibrations is not natural frequency, it is frequency of vibration is called a driving frequency. It's called driving frequency. The frequency of this box is natural frequency, but now it is vibrating with the frequency which is provided by this tuning fork. Therefore, it is called as a driving frequency. Usually, this driving frequency is denoted by F. Here, we denote it by Fd. Now, the third point, we note that when tuning fork is held on the top surface of this box, there is no loss of energy. Up to as long as the tuning fork is there and it is in vibrating condition, then there is no loss of energy in that small time interval. Amplitude also remains constant. Here we can write the third point as there is no loss of energy. And fourth point also we note that amplitude remains constant. Amplitude remains constant as long as there is driving force is present. We can write it clearly like this: as long as external periodic force is there. External periodic, not only force, it is external periodic force. Force is present. This is the point we have noted from this simple experiment. There is no loss of energy. Amplitude remains constant, but it is constant as long as periodic force is present. Now, when we consider the example of box, here hollow box, and there is a tuning fork, it is having frequency FD, and for the box there is its own frequency, that is Fn, it is natural frequency. It can vibrate with its natural frequency also, and Fd is the driving frequency. Now there is difference between, means values are different, but we can have the tuning forks having different frequencies. We can use that frequency here. If we perform some experiments, in that we can vary the frequency of external periodic force, then it affects the amplitude. So in the fifth point here, one more point is related to amplitude, that here amplitude depends on the difference in driving frequency and natural frequency. Depends on difference in frequency. Difference in frequency. So this point is slightly difficult to understand, but try to understand it that if there are two bodies, one is vibrating body, means externally vibrating body, and other body is we have to vibrate it by the external periodic force, then both are having different frequencies initially, but if we consider the difference, then amplitude depends on that difference, and it is related, or we show on the graph, it is like this. Suppose there is x-axis showing the frequency of driving force and y-axis showing the amplitude. Then it is observed that if this driving frequency is made exactly equal to natural frequency of vibration of a body, then amplitude we observe as maximum. A is maximum, A max we can observe. Maximum amplitude is denoted by A max. And if the frequency is less than natural frequency, then amplitude is small. If the frequency is greater than the natural frequency, then also amplitude is small. But if the driving frequency is close to natural frequency, if Fd is close to Fn, or Fd is exactly equal to Fn, then A is maximum. A is maximum. Graphically we can perform such experiments, but try to remember this graph, that for the frequencies which are less than natural frequencies, amplitude is small. Greater than natural frequency, the amplitude is small. But at a particular frequency of driving force, that is Fd equal to Fn, then amplitude is maximum. Here you have to show it is A max. Now this case of forced vibration is a special case and it is called as a resonance. Resonance is a special case of forced vibration. You can make a note here that resonance means the forced vibrations, but in which frequency of driving force is equal to the natural frequency of the body and amplitude of vibration is maximum, then the body is said to be in resonance. Here the sounding box is said to be in resonance if its frequency means natural frequency is equal to the force of frequency of tuning fork. If it becomes same, if the frequency matching is there, then amplitude is maximum. So this point again I will explain by taking another example. So, but before going to that example, you have to note these points which are related to free vibrations and forced vibrations. So you note this difference and then we go to the next point of resonance by considering another example. So try to note these points. Now we have considered one example, that is the sounding board and tuning fork. Now we consider a system of pendulum. Here there is a system of 4 pendula. Pendulum is singular, pendula is plural. Here there is pendulum A. There is another pendulum B. Clearly here LB is less than LA. There is third pendulum which is denoted by C. Here LC is equal to LA. Means we conclude here that by the theory of pendulum that frequency or period of C is equal to period of A, or frequency of C can be equal to frequency of A. There is fourth pendulum is denoted by D. Now if pendulum A is set in 2 vibrations in this way. This is the line of vibration and pendulum is vibrating perpendicular to plane of figure, but we have shown it the line for the sake of understanding. We have shown it like this. Then what happens when we supply energy to A? When we disturb the position of A, then it starts vibrating. Its energy is received by the string. To this string, here all pendula are supported. The energy is received by B, the energy is also received by C and also received by the D. So B starts vibrating with some amplitude. Here B vibrates with a small amplitude. D also vibrates with small amplitude, but we observe that the pendulum C vibrating with the amplitude which is same as A, because the lengths are same for A and C. Frequency of vibrations also becomes same after some time, and this C receives more energy from A than B and D. As frequencies are same, pendulum C receives more energy than B and D. Therefore, amplitude is large. Amplitude is large here. So, amplitude is large and frequency matching is also there, because A is here driver pendulum. It is driver or it is driving force. Driving force is given from pendulum A to B, C and D. Therefore, it is also called a driver pendulum. This driving frequency becomes equal to the natural frequency, means here Fd is the driving frequency, or simply it is driving frequency, and this is the own frequency of C. Fc is equal to Fa. Frequency matching is there, amplitude is large, then we say that A and C, or C is in resonance with pendulum A. We have to complete the sentence here. Pendulum C is in resonance with pendulum A because their frequencies are same and amplitude is large. So this is the condition for resonance. All pendulum are vibrating. B and D all are having forced vibrations, but C is having special type of vibrations for which the amplitude is maximum and frequency is same. Therefore, for the pendulum C, we call those forced vibrations as resonance. So pendulum C is in resonance with pendulum A. Now here, this is one example for the understanding of forced vibrations as well as resonance. So when the energy is given to A, when it is vibrated, it acts as a driver pendulum. It acts as a driving force for all other pendula B, C and D. But here C is having same length, means its frequency matching is easy, and as frequency matching is there, amplitude of vibration is large. For B and D, amplitude of vibration is small. Those vibrations are forced vibrations. For C also the vibrations are forced vibrations, but they are special. Here showing the frequency matching as well as amplitude is maximum. Therefore, we have to say that pendulum C is in resonance with A. So this is the discussion about forced vibrations and resonance. So you have to make the note of resonance by taking the 2 points, that it is the special case of forced vibrations, forced vibrations, and in which frequency, second point we write driving frequency is equal to natural frequency. So you can make the sentence here. Amplitude is maximum for the given body. Energy is maximum. This phenomena is called as the resonance. So today we stop here. Thank you.